So let's consider the following integral here. One thing that really stands out here is that 3x squared, and we know that that is the derivative of x cubed, right? Bring down the 3, subtract 1 from the exponent, you get 3x squared. And in fact, it's the derivative of the entire bottom here, because the derivative of 3x, or the derivative of x cubed plus 1 would just be 3x squared. That plus 1 would go away. And so you could, let u equal x cubed plus 1. And so your du in this case would be 3x squared dx. And so there's your 3x squared dx. And you'd put a u down there, and so this would just equal, just substituting things in, you would get like 1 over u du. So in for this, I'm putting in du, in for that, I'm putting in u. So I get this, and that's just the natural log of the absolute value of u plus c, and then I can put u back in, and I get natural log of x cubed plus 1, and that plus c. Okay? What I want to do here is I want to show you that there is kind of a general rule. What you see in this is that the numerator is the derivative of the denominator. And you could make this rule, you could call this the log sub rule. I've never heard it called that. I just made that up. The log sub rule or something like that. And it's basically, if you have this f, you have the derivative on top and the function on bottom, like this, then this is just going to be equal to the natural log of the function that's on the bottom, plus c. That's a nice rule. So pattern recognition, if you see a function on the bottom and its derivative on the top, you can just jump right over here. And we could even make a little proof of this if we wanted to. I could say that this we could rewrite it as 1 over f of x, and then f prime of x d of x, and then I'd let my u be f of x, then my du would equal f prime of x dx, and so this would become du, this would become u, so I'd get 1 over u du, and that would just be equal to the natural log of u, absolute value of u, plus c, and then plugging the u back in, absolute value of f of x plus c, which is what this rule says. So, so this is a nice way of thinking about these sorts of antiderivatives where you have a ratio and you have the derivative over the function. You can go right over to here. So let's just try a few examples of this. So if I'm looking at this, if I take the derivative of the bottom, I get 2x minus 3, and then everything, the plus 1 goes away, and that's what I have on top. So my top is equal to the derivative of the bottom. So real nice and easy. This is just the natural log of the absolute value of x squared minus 3x plus 1. All of that plus c. Isn't that nice? Okay, well look at this. This derivative here, if I take the derivative of the bottom, I get 3x squared plus 3. Now, let me write that up here. 3x squared plus 3. Well, what do you notice here? That this isn't the derivative, but if I factor out that 3, I get the x squared plus 1. So if I had a 3 here that I could multiply through, then I would get the derivative. So I could rewrite this as 1/3, and then I would have 3, and then you'd have like the x squared plus 1 all over x cubed plus 3x minus 5 dx. So in other words, if you distribute that 3 now, so bringing that 3 out, that would just cancel out and become 1, right? And you get the original one. So in other words, I multiply top and bottom by 3, move out the 1/3, distribute that top portion, and I would get like 3x squared plus 3. This is x cubed plus 3x minus 5 dx. And now I have something I can use my log rule for. I have the 1/3 natural log of the absolute value of the bottom. Nice. Okay, so it wasn't quite the derivative, but I could, if I can multiply it by a constant and get the derivative, then I can just put 1 over the constant on the outside. Okay. Now, look at this. This does not look like, it looks something like something very complicated you'd have to figure out. But what I recognize here is that secant squared x is the derivative of tangent of x. Okay, so I don't have the derivative here on top, but the derivative of this bottom, because if I took the derivative of the bottom, the 5 would just go away, and I'd get 3 secant squared x. So basically, I could rewrite this. I could have a 1/3. I'm not sure why it's always a 3 there, but 1/3, and then I'd have 3 secant squared x over 5 plus 3 tangent x dx. Now, when I take the derivative of the bottom, I do get the top, and so I can rewrite this 1/3 natural log of 5 plus 3 tangent x plus c. Okay, so that's nice. And now, when I look at this, this looks really complicated, but if I remember the derivative here, the derivative of the secant of x is equal to the secant x tangent x. So the derivative of the bottom is equal to the top, and so I just get the natural log of the bottom, making that quite easy. So what looked really complicated in this case ended up being quite easy. Okay. So now what I want to do is I want to prove, so I can use this quite easily to prove the derivative for the, or the antiderivative for the secant of x dx. So what this actually ends up being is the natural log of the secant of x plus the tangent of x plus c. That's what it ends up being. So if I have the natural log of this here, then it kind of seems like if I had a secant x plus tangent x on bottom, and then the derivative of that on the top, that would lead to this, using that natural log rule. And so what I'm going to do is, I'm going to do the little trick of multiplying the top and bottom by the same thing. And what I'm going to multiply it by is what's inside here. How you would have known to do that, I don't know. But now that we know that we can do that, what I'm going to do is distribute that secant of x through. And when I do that, I actually get secant squared x for this plus secant x tangent x all over secant x plus tangent x dx. And then commuting those two around, it doesn't matter. Addition is commutative. The derivative of tangent x is the secant squared, and the derivative of the secant x is secant tangent x. So the derivative of that bottom is equal to the top. And so using my natural log rule, or my log sub rule, or whatever, I get the natural log of the bottom. Secant x plus tangent x plus c. And there you go. I've just derived the antiderivative for secant of x. It's equal to this. Okay. So really cool stuff. So that natural log rule, or log sub rule, or whatever, can be useful. It's pretty useful in situations where it arises, and it does arise from time to time. So so in the final video, we're going to do some harder trig subs that aren't as obvious, and in particular, we're not going to necessarily have a composition of two functions where the derivative of the inside function is hanging around somewhere on the outside. It's not going to be that sort of u substitution, okay? But we are going to be able to do a substitution. As long as we do it consistently, we're going to find if our substitution helps us take the derivative, we have a method then for using the substitution method to find derivative of other functions.